Good afternoon, everyone. Uh, Welcome to the workshop. I would like to begin by thanking Rose, Picard, Akane, and other organizers of the workshop for inviting me to deliver this keynote address. I apologize that I can't be there in person as we are hosting the annual meeting of MD2K, where guests are arriving right this afternoon as you hear this presentation. But I hope to see you at some other time. So next, let me get started in the interest of time so that we can keep things on schedule. I'm going to describe to you my research related to mobile sensor big data for monitoring and improving health, wellness, and performance. Uh, Before I proceed further, I would like to acknowledge the support of our sponsors, National Science Foundation, IARPA, and National Institutes of Health, in particular the Big Data to Knowledge Initiative, Office of Data Science. So MD2K Center of Excellence that I'm fortunate enough to lead consists of several partner institutions across computer science, electrical engineering, statistics, behavioral health, and medicine. We are very fortunate to have an amazing set of 20 investigators from these universities. Then this entire center is run from University of Memphis that has 6 staff members, 3 software engineers, a postdoc, and 10 graduate students. Altogether, the MD2K Center involves about 70 investigators, students, and postdocs and staff members. So the work that I'm going to describe to you has had significant contributions from many members of the MD2K Center. So let me first begin by reviewing for most of you, I believe, the health and wellness potential of using mobile sensors. Mobile sensors now appear in a variety of different devices that people carry in their daily lives. Mobile phones, the most pervasive mobile device that has many sensors built into it. Then activity trackers and smart watches, which can measure arm movements, then chest bands that can monitor physiology, and eyeglasses that can measure visual exposure of the individual as well as measure movement of the head and pupil movements and so on. So these sensors taken together, they can help measure exposures in the natural field environment, whether it is exposures to sedentary behavior, exposures to traffic jams, exposure to alcohol, tobacco, fast food, various other risk factors. They can also measure daily behaviors such as activity, eating, smoking, conversation, alcohol usage, drug usage, etc. And so while exposures and behaviors, they form risk factors, they result in changes in the health state of the individual. And fortunately, mobile devices, they can also help measure some of the outcomes of these risk exposures. For example, they can help measure stress, congestion in congestive heart failure patients, depression, that's directly related to the mental health, the topic for this workshop, seizures, Rose Picard's work, and also oral health behaviors. So if mobile sensors can help measure both risk factors and their effect on health, all in the natural field environment on a continuous basis, they present a very powerful platform that can help with early detection before irreparable damage happens to end organs. They can now, since they are measuring both the changes to the health state as well as the risk factors that may have contributed to those changes, we can mine the data set of risk factors and try to pinpoint those factors that may have the largest contribution to adverse health effects and use those to develop interventions so as to predict and prevent adverse health effects before it's too late, and truly realize the vision of preventive medicine. Also, since mobile devices, they are aware of our environment or context surrounding us, they can time the interventions and treatments so as to ensure that we are most available when those interventions and treatments are delivered to have maximum chance of efficacy. These mobile devices, since they can measure the change in health state, they can also personalize the treatments by monitoring both the receptivity and the impact of interventions, and then and cycle through and determine the most efficacious interventions that works for each individual, and thus help contribute to the realization of precision medicine. I can briefly describe two examples from the MD2K Center of Excellence's work. One is smoking cessation. So in the smoking cessation, the difficulty has been to detect when somebody who is trying to quit has a first lapse. And if a smoker who is trying to quit has a first lapse, in more than 90% of the cases, though, they go back to becoming a full smoker again. And so, if there can be a way to detect first smoking lapse using mobile sensors without the individual having to inform the study coordinators or their therapists, then there is a chance that we can launch interventions right upon the detection of first lapse and try to bring the person back to full abstinence phase. Uh, and then it'll be even better if we can find a way to detect high risk situations that may lead to first lapse and use those detection of high risk situations to launch interventions and prevent the first lapse itself. That will be a big win. And so that we can also do by monitoring the first lapse, detection of first lapse, and then looking in a research study with participants who were trying to quit, and look at what factors contributed to the first lapse, which could be stress, could be exposure to tobacco outlets, could be exposure to seeing others smoke, or to passing through a public smoking spot, or to exposure to alcohol. So there may be a variety of factors. So if we can determine the factor that may be most vulnerable for an individual, we can launch various interventions, help them avoid those risky situations. Another example can be congestive heart failure. So whereas the smoking cessation causes the most death, congestive heart failure is the highest cause of readmission. So if we can find a way to reduce the rate of readmission, it can help the patients, it can help their family members, it can help the healthcare system. So everybody wins. So for the early detection for congestive heart failure patients, there is a new sensor called EasySense developed by my colleague Emre Ertin at Ohio State University that uses radio frequency waves to estimate the level of congestion by determining the fluid accumulation in the lungs. So that when combined with other data such as activity detection and uh, and then eating behaviors or weight measurements and blood pressure. So these data together, they can help get a reliable estimate of growing congestion, and which can then be used to increase the diuretic dosage of their medication and help prevent readmission. Uh, it will be again even better if we can try to find those factors that may lead to increase in congestion, such as say high salt intake, and show to the patient themselves the effect of their own daily behaviors. If they walked more, that their congestion reduces. If they had more salty diet, their congestion increases. And this can go on to motivate the participants to adopt healthy behaviors, and that can go on to improve their health and again prevent even a situation of readmission. So our approach to develop each of these markers, whether it is for early detection or it is to find the predictors, has been to allow collection of high frequency sensor data in the natural field environment, which can then be used to both develop and validate biomarkers, and as well as develop and validate or test sensor-triggered interventions. This is akin to biomedical research, where instead of just storing the assays, uh, biomedical researchers, they archive biospecimens, which can then be used to conduct a variety of different assays after the research study is completed. Similarly, in research involving mobile sensors, if instead of only collecting the assays, in this case will be activity counts or distance walked or calorie burned or stress levels, we collect the raw sensor data itself with appropriate labels. Then the same sensor data, for example, if it is from wrist sensor, uh, the same data that is used to count steps and estimate calories can also be used to uh, measure hand-to-mouth movements, which can then be fed into models that detect smoking or eating behaviors, or even oral health behaviors. So in summary, collecting the raw sensor data with appropriate labels can help greatly with respect to development and validation of new biomarkers, as well as increasing the research utility uh, of the sensor data that is collected and advanced data science too. So in MD2K, there are several sensors that we use to collect the sensor data. There is a chest band called AutoSense that includes various physiological sensors. Then there is a wrist sensor that includes both inertial sensing for hand-to-mouth movements, as well as pulse plethysmography for estimation of intrabeat intervals. Then Easy Sense that I briefly talked about. Then various phone sensors, then smart toothbrushes, weighing scales, blood pressure. So these are various sensors that we use in MD2K studies. From the data that we have thus far collected in various field studies, we have developed models to detect smoking, stress, craving, drug use, conversation, and several others. Given that this workshop is on mental health, I thought I can talk about a particular example, which is how did we go from developing a model to detect stress to developing a stress sensor triggered stress interventions. So this process consists of the following steps. First is the sensing. So we collect these data from ECG and respiration and accelerometer from the chest sensors. That results in several million samples per day. When participants wear these sensors during their awake hours in the natural field environment. From those data, then we estimate both the likelihood of being stressed from physiological arousal, as well as the likelihood of these physiological activation resulting from physical activity. Then, so this reduces these millions of samples to thousands of samples per day. But if we are to launch interventions, we can't interrupt a person even tens of times per day, let alone hundreds or thousands. So from all these thousands of data samples, which we obtain from these millions of data samples, we have to find those one or two opportune moments throughout the entire day when an intervention should be launched. So one has to find those one or two intervention opportunities from this millions of original data samples. So that, in a sense, is a challenge in developing these sensor-triggered interventions from data collected in the natural field environment. So I'll go through each of these steps. So first, for C stress, this is covered in a UVCOM 2015 paper in more detail, but I'll just quickly summarize it. So we developed a model to convert ECG and respiration sensor data into a continuous measure of stress. The input is a vector of 1 minute measurement worth from ECG and respiration, and the output is a stress non-stress level or of alternatively probability of stress. We use a support vector machine model and and we validated it on various independent data sets. So the other, one challenge here in assessment of stress is that during active, when participants are active physically, then the physical activity demands increase the physiological activation, and that may confound the measurement of stress. So typically data just after physical activity that can be detected with accelerometers are discarded so as to allow for recovery, so that we have clean data for assessment of stress. So if we use this simple measure of discarding 2 minutes, of data after each physical activity will end up discarding about 57% of total data, 22 or 23% due to when people are actually already engaged in physical activity, and additional 35% because of those 2 minutes. So students developed a model to estimate the time to recover from physical activity so as to reduce the amount of data that is to be discarded after each physical activity episodes. So for the training and validation, so one major challenge is that how do we know when the person is stressed, as opposed to say eating or smoking or drinking, when one can observe and if unequivocally be able to say when this event occurred. Stress is something that is perception, and therefore it's pretty hard to say when this actually occurs and when this not occurs. So the ground truth is one of the first difficulties. So for ground truth, we use the lab data. In the lab, participants were engaged in public speaking, mental arithmetic, and cold pressure that is known to stress most people. So when a person is within the lab session and under public speaking or preparing for public speaking or doing mental arithmetic, those minutes of measurements are the ones that we label as stressed. And when they are under recovery or under baseline, watching nature videos, those are labeled as non-stressed. The second challenge is that physiology has a different rate of recovery than perception of stress. Physiology typically recovers quickly, but the perception of stress in a person's, for a person may linger much longer. If you like, you can recall anytime you had a traffic scare, your heart rate might have jumped at that, but it subsides soon as our parasympathetic system kicks in. But we may feel jittery even several minutes after that. So, in the field, the only measure we can obtain are the self-reports, and self-report captures only perception of stress. So, it's hard to pinpoint a self-reported stress level corresponds to which minute of physiological data. So, if a stress episode occurred, like let's say notification of a paper or a grant proposal, 10 minutes ago, then physiology may have recovered by the time we solicit self-report, but the perception of stress may still be high. And so we developed a Bayesian network model to map this minute level output from C-stress to self-reports for field validation. So, once we had these models, we had self-report in the lab as well. And so we first used this labeling of data, physiological data from the lab protocol to develop this model, and then applied the Bayesian network model to validate with the self-report. So first, just the lab validation part. For lab validation, as you can see, the main finding I would like to highlight here is that typically, heart rate variability is used as a surrogate measure of stress. And if we use only heart rate variability related features, then you see the F1 score is about 0.56. But if you use if we supplement the heart rate variability with several other features from ECG, like 80th percentile of R2I intervals or median interbeat intervals, then the F1 score becomes much higher, like 0.78. Second point I would like to mention is that when we do this field validation with self-report from EMA collected in the field that prompts the participant several times in a day, then there is a level of consistency within the self-report, meaning how we have several items in the self-report that try to obtain the same sense from the participant, and there is a measure of consistency across those items points to how well or how accurately could we try to match the self-report, because it's kind of upper bounded by the consistency among the self-reports themselves. So The median F1 score that we see for each participant, we had several self-reports. So for each participant, we computed an F1 score, meaning how well our model was able to predict the self-report that will be provided by the participants. And so we had a median F1 score of 0.71 in the field setting. And again, in the field setting, the participants that we had were different than those did the lab test. So that was an independent data set. We tested this model on another independent data set where participants wore the sensors for, so in the previous case, it was 1 week of field reading. In this case, they wore it for 4 weeks. And here also, we find that the median F1 score is about 0.72. And when we sort the participants on this median F1 score, we find that the Cronbach's alpha score, the consistency among self-report among the 5 participants on whom we had poor F1 score, see that that's pretty low. So that means their self-report may not be as reliable. So part of the reason why we don't get a good F1 score on this. So next, we want to find those few time points when the stress level of the participants is high enough that it should be used to deliver a intervention. So for that, we use this stress likelihood time series to develop another model to identify those few time points in the entire day when a stress intervention should be delivered. So what you see here, the y-axis is the stress likelihood, and you see the values of likelihood of stress from various participants. The red means that these measurements come from a session when they were under a stress session, and green ones they were not under a stress session. So we come up with one threshold that can be used to decide, stress versus non-stress. There'll be some false positive and false negatives, but in general, it provides a good performance. So next, what we do is we take this time series of stress likelihood from the field data or from the lab data, and then create this smooth that time series to reduce the variability, and find this stress density, which is area under that curve, the time series of stress likelihoods. We use this MACD, moving average convergence divergence method, to find the inflection points when the stress likelihood begins to rise, and then when it begins to fall, and then begins to rise again. So next, what we want to do is we want to find those time points when, which may be opportune moments to trigger intervention. So we want to find those stress densities that are high enough, which should be used to trigger stress interventions. When we do so, we have several opportunities. We can trigger, A, B, C, and D here on the right curve points to various opportunities we can use for stress interventions. If it's D, we know the stress episode has occurred in the recent past, but it is now over. So that could be a reactive stress intervention. At C, we know the stress level has peaked, just slight bit past the peak time, and that there could be that could be another opportunity to launch a stress intervention to try to calm the person down. But at that point, the person may be under stress and may not be as receptive as would be at point D. You could also try to have proactive interventions at point B or point A, but notice that at point B, we don't know the future. We don't know whether this episode indeed will become a significant stress episode or not. So this becomes much more challenging problem in terms of having high accuracy. So there may be more false positive in such cases. So we went back to the lab data set to try to find the appropriate stress densities, which should be used to launch this stress interventions. And so this time, we try to come up. So what you see here are, again, the red ones and green ones similarly correspond to when the person was in the stress session or not in the stress session. But here the y-axis now is the stress density of each of the episodes that occur in the stress likelihood time series. So to be sure that the individual is indeed being under stress, because we want greater certainty before launching intervention, we came up with one threshold that is able to detect the stress occurrence with higher confidence or with a given confidence, and similarly for not stressed with a given confidence. So we may have some unsure category which can be left out for stress intervention. So here we provide some examples of for various desirable precision and recall values, what values of thresholds we come up with, and if we use those thresholds, how many the three rows at the bottom describe how many episodes of stress and non-stress or unsure we observe to occur in the field. In fact, so I just went through the entire example to showcase one particular approach of delivering stress intervention from the sensor collected data. I can now briefly describe various challenges that happen in this kind of work. First, during the marker development itself, first challenge is having reliable data. Second challenge is that of developing the right model. Third challenge is that of computational efficiency so that these markers can run in real time on the phone without draining the battery. And fourth is how do we validate these models in the field environment where they are supposed to be deployed. So for collecting the mobile sensor labeled mobile sensor data with high frequency mobile sensor data, there are several requirements for such a platform. Like it should be able to connect to diverse sensors, support high frequency streaming data, and storage can support this high frequency quick data that accumulates very quickly. We should have real-time data quality monitoring so that we can fix the sensor attachment issues, real-time computation of biomarkers, and then collection of these labels, or by notifying the participants or launching interventions. That should all be supported by platform. So I'd like to mention that we have developed a platform in the MD2K Center called mCerebrum. It's fully described in a Census 2017 paper. That is able to fulfill all these requirements. You're welcome to learn more from the paper. But in general, it is able to support 70 plus million samples of data collection per day, has a built-in privacy controller, has a real-time data quality monitoring, has the ability to compute biomarkers in real time and use those to launch self-reports or interventions. And this is all available open source. It is currently being used to run about 10 studies at 10 different sites, and this entire ecosystem, the sensor software and the cloud, should be available very soon to the entire community. It has a very modular architecture, so it should be possible to add in or plug in new apps on the phone, as well as connect new sensors onto this or replace any of the data analytics modules. Others. So the key innovations in mCerebrum, one is, first is that the data exchange architecture we have come up with supports, high data rate. Data and computation reuse allows for this high frequency data collection as well as real-time computation from those data. We have our collaborators at UCLA, they have come up with Pebbles, which is a append-only scalable storage for storing this high frequency sensor data. We use micro batching for efficiency in data ingestion so that the phone can last much longer despite doing this heavy duty work. And we have several real-time computation of biomarkers done on the phone itself, and all of that code is available. And then the system supports this biomarker-triggered notification interventions. Another issue is that of data diagnostic. That means if the data collection is not going well, to be able to figure out what specific factors might be responsible for it. Again, this is described in more detail in a BCB 2014 paper. Yet another issue is that if suppose we are doing a study on, say, smoking cessation or cocaine usage, what we care more is having data collected around these critical events of interest, whether around the first lapse or in the cocaine use or cocaine use episodes. So say, in the first, what we show here is that the challenges that how much data is lost, even though we may have more than 10 plus hours of data per day. we may not have data around the events of interest, sufficient data around the events of interest. So, for example, in a smoking labs smoking case, people may go out to do a smoking and come back and leaving the phone behind, which may lead to the phone and sensor getting disconnected and not having enough data. The modeling challenges itself, uh, we need to come up with the right theories that we don't yet have, which have been the case in computational linguistics or computer vision or text mining, where there are several important theories have emerged that have allowed for theoretical advances in mobile health space. We need to come up with those appropriate models or appropriate mathematical models that can help development of theories and advance the data science. Validation itself is a challenge, because any of these models we come up with, let's say for smoking, there isn't anything equivalent that can do this detection of smoking reliably in the natural field environment. So finding the temporal accuracy of what we are detecting with these mobile sensors, that its validation in the field is a significant challenge. Uh, and then sensor triggered mobile interventions, there are several issues there. One, when do we trigger the interventions? When is the person? That's the one I talked about, as to finding those opportune moments when interventions can be launched for stress. Now, if there are multiple such triggers like geolocation or geofencing and eating and smoking and stress, then how do you combine these multiple sources to come up with those few moments when intervention can be delivered? Then we also need to find out if the individual is available mentally, physically, and socially to be able to receive interventions. Then we need to come up with cyber physical system models to have theoretical basis for these interventions. So meaning that we have now computational methods for for these closed loop systems like insulin pump or pacemakers or neural stimulation, but doing so for this behavioral intervention, is still a big challenge. There are successful examples of complex cyber physical systems, but the one for behavioral intervention is yet to emerge. Then, if our participants to wear the sensors continuously, then there is need for a killer app that can naturally motivate participants to wear the sensors. And so we need to come up with short-term benefits that people will have in addition to the long-term health benefits. Finally, very quickly, I would like to talk about the mPerf project that we have recently started working on for modeling and predicting the everyday job performance using mobile sensors. So work performance is one of those things that it's the place where people spend majority part of their awake life, and has one of the largest determination or largest impact on the financial well-being of individuals, which again affects the health and well-being. So if we can help people improve their work performance, and that can greatly go the distance to help them improve both their satisfaction, quality of life, and then which can spill over to improving their health and wellness. So in this project, our goal is to use the same mobile sensors, but to obtain markers of work performance, personality, as well as the citizenship behaviors. So this is a project that we have started working on. In few months, we should have data, and let's see how well we are able to model and predict the work performance. But that again presents another interesting challenge for the community. So in summary, mobile sensors can help people live healthier, wealthier, and happier life. And there are numerous challenges in here to provide dissertation ideas to all the upcoming students. There are several training resources from MG2K. All the software we have developed, both for mobile phones as well as for the cloud, they're all open source and available on GitHub. We have an mHealth hub that provides a lot of dissemination information for lectures, courses, as well as meetings and software forums. We have mHealth Training Institute that is held at UCLA every year, that trains up and coming researchers to work in interdisciplinary teams and how to jointly write interdisciplinary proposals. And here are the links for any further information that you'd like to get. Thank you, and I can take some questions.